Okay, so we're going to pick up with this calculation we started last time. We're looking at a spherical balloon inflated with helium to a volume of 30 cubic meters. And if the pressure is 740 torr, and the temperature is 27 degrees Celsius, what is the mass of helium in the balloon? So here we're using the ideal gas law to begin with. All right, so we're using this PV is equal to nRT. We calculated last time the pressure in terms of, we calculated the pressure in terms of atmospheres, because that's how our ideal gas constant R is related to us. We also calculated the volume in terms of liters, again, because we have liters and atmosphere, so we want to make sure that our pressures are in atmosphere and our volumes are in liters. And then our temperature we converted to Kelvin there right at the very end. So let's put down the things that we know on our next slide, and we can finish up the calculation here. So we've got, so P, V, N, R, and T. So the pressure we calculated to be 0.9737 atmospheres. The volume we calculated to be 3.00 times 10 to the 4th liters. N is what we're looking for still. R is 0.08206 liters atmospheres per mole Kelvin. And our temperature we calculated to be 300.2 Kelvin. And so what we can do here is, understanding that we're using our ideal gas law, PV equals nRT, we could rearrange this to solve for N such that N is equal to PV over RT. And we can plug in our values to solve for the number of moles of helium. So we can say, so N is equal to 0.9737 atmospheres times 3.00 times 10 to the 4th liters divided by R, which is 0.08206 liters atmospheres per mole Kelvin times 300.2 Kelvin, right? And so you do that, you plug that into your calculator. The atmospheres and atmospheres cancel, liters and liters will cancel, Kelvin and Kelvin will cancel. And we have, notice, moles in the denominator there. So if it's in the denominator of the denominator, it gets flipped into the numerator, and we wind up with a value for the number of moles being 1,185.8 moles of helium. And since we had the number of significant figures will be 3 because of our limitation here with volume. So I'm just going to underline that value right there. So that tells us how many moles of helium that we have in this container, right? But the container asks for specifically, right, the mass. Well, once we know moles, we can determine mass, assuming we can figure out the find the molar mass of that substance. And for the case of helium, right, we know that helium is 4.003 grams per mole based on our periodic table. And so we take the moles, 1185.8 moles of helium, right, where we have, there's our sig fig. Multiply that by the molar mass, 4.003 grams of helium per mole of helium. And you wind up with value of 4,746.7 grams of helium. And of course, we can round that to the proper number of significant figures. So 4,750 grams of helium. All right. And so that sort of ties that up. But basically, in this case, we used our ideal gas law to figure out the number of moles of our gas. And then from the number of moles of a gas, we're able to determine its mass. So basically, because it doesn't matter what gas you have, the higher the molar mass, right, the higher the mass is of that gas. And so the higher the larger the molar mass of the gas, you can think of it as being the larger the density of that gas as well. Okay, so that brings us into our next section, this time on gas stoichiometry. So when we look at gas stoichiometry, we're now looking at really moles of gases that react with moles of other gases. And so when we've done stoichiometry in the past, we've always figured out moles, whether that was if we dealt with a solid, we started with mass, we determined number of moles by dividing by the molar mass. If we started with a solution, we started with a volume and a concentration, we figured out the number of moles by multiplying the volume times the concentration. For gas stoichiometry, we're often going to take and determine the number of moles from the volume, the temperature, and the pressure. And so a lot of the chemistry that we do is done at what we call a standard temperature and pressure that allows us to do much easier comparisons between reactions. So standard temperature and pressure, or STP, as it's abbreviated, is just a set of conditions for a given gas. And it's a standard temperature, it's something you would find if you have data in a table somewhere that you would collect that data at standard temperature or pressure. And for a gas, the standard temperature is going to be 0 degrees Celsius, and the standard pressure is 1 atmosphere worth of pressure. Those are our standard values. And so when we consider a gas at standard temperature and pressure, we can actually calculate, if I have 1 mole of an ideal gas, we can determine what volume that mole occupies at standard temperature and pressure, and just by multiplying using PV equals nRT, right? So we've got the volume is going to equal the number of moles times R, so nR, and T, there's our temperature at 0 degrees, divided by the pressure. And you wind up seeing that 1 mole of an ideal gas will occupy 22.42 liters at standard temperature and pressure. And so we call that the standard molar volume of an ideal gas, the 22.42. And that's something we can use in order to do comparisons of gases, maybe reactions of gases that take place together at a standard temperature and pressure. So we can do those direct comparisons in the actual chemistry of a reaction. And so we've got some examples we can look at, basically very simple examples. The first one we're going to start with is if you have a sample of nitrogen gas, it has a volume of 2 liters at standard temperature and pressure. If you know the volume, the temperature, and the pressure, you can determine the number of moles. And we can do this really 2 ways, right? We can determine moles just like we did, right? N is equal to PV over RT. And you can plug in those values, assuming you remember the standard temperature and pressure values. So pressure would be 1 atmosphere. Volume we're given 2.0 liters. R 0.08206 liters atmospheres per mole Kelvin. And then the temperature will be 273.15 Kelvin. And so you can do that calculation anytime, right? You can use your ideal gas law to calculate that, and you wind up with a value, right, 0.08921 moles of N2, and you have 2 sig figs because of the 2 liter volume, so really 0.089 moles of N2. Okay, so that you could do it that way. That's one way. But you could also, assuming you know the standard molar volume, if you know the standard molar volume is 22.42 liters per mole, right? That's the volume that 1 mole of a gas occupies at standard temperature and pressure. You can actually just say, well, 2.0 liters at STP divided by the standard molar volume will give you the number of moles. Okay, so you can do this either way, right? If you have that standard molar volume, that's likely to save you a little bit of time as you're doing some calculations. Okay. All right. But we can now use our understanding of stoichiometry from more than just the PV equals nRT standpoint. We can apply things that we know in the past. So for our next example, we can go and look at, in this case, 1.3 grams of dry ice. And if you put it in a balloon, remember a balloon is a flexible container, so it's going to expand until the pressure inside and outside the container are the same. In this case, the standard pressure is 1 atmosphere. And so we can calculate the volume that would occupy, assuming we know the number of moles. Here, if I've been given a mass, right? If I know the mass, I can calculate the number of moles. And so if I know the number of moles, I can use that standard molar volume to figure out the volume that it occupies at STP. And so here we have 1.3 grams of CO2. We can convert that into moles by dividing by the molar mass. Okay, so the molar mass of carbon dioxide is, if you use your periodic table that's available to you on Canvas, right, it's 44.009. There we go. Grams of CO2 per mole of CO2. All right, so our units will cancel. We'll figure out the number of moles. We wind up with 2.954 times 10 to the minus 2 moles of CO2. And sig fig wise, that should be rounded to the second decimal place because our 1.3 grams of dry ice. Now, if we know the number of moles, we can just plug that in using our standard molar volume. You can also use the ideal gas law if you choose to, but really if you memorize that to 22.42 liters per mole, that can be really useful, particularly in a case like this. So take your 2.954 times 10 to the minus 2 moles of CO2, multiply that by the standard molar volume, 22.42 liters per mole. You wind up with a value of 0.623 liters. And since our number of moles had 2 sig figs, our answer should have 2 sig figs, so 0.66 liters. Okay. So again, we're using that stoichiometry, the stoichiometric relationship between volume and number of moles in this case. Our next example, so what volume of oxygen gas is at standard temperature and pressure is required to react stoichiometrically with 24 grams of methane. So now we're doing stoichiometry with gases and chemical reactions. And so part of this is understanding what type of a chemical reaction it is based on our experience in the past. Right? If we have methane, you should by now know that methane is CH4. That's one of those compounds you should absolutely have memorized by now. So methane, so CH4 gas, plus oxygen gas, O2 gas. Well, this is a a combustion reaction. So we know that this is going to react to form CO2 plus H2O. Right? And since this is a chemical reaction, we need to make sure we balance it. Of course, we have done this one in the past, so we should know there's a 2 there in front of the oxygen, and there's a 2 there in front of the water. Now from this, it's a simple matter of converting initially the number of grams of methane into moles of methane. And then from the moles of methane, we can figure out how many moles of oxygen, and from how many moles of oxygen, we can figure out the volume of oxygen that's required. So here, we take our 24.0 grams of methane, divide by the molar mass of methane, which if you calculate that using your periodic table, you wind up with 16.043 grams of methane per mole. Okay. And so that right there will get you into units of moles of methane. And I'm just going to directly go into the next part of the calculation, because if our units are in moles of methane here, we can convert to moles of oxygen by the mole ratio. So we know that for every 1 mole of methane that gets used, that we use 2 moles of oxygen. And then to figure out the volume, we just utilize that standard molar volume, 22.42 liters per mole, okay, of O2. So our units will all cancel out. We'll be left with a volume at the very end. And so we'll find that that right there, if you do that calculation on the way through, you should get 67.1 liters of O2. And so again, this is just a stoichiometric calculation for this particular chemical reaction, right? And now we're just getting to moles in a slightly different way. We're getting from moles in a slightly different way and converting between moles and volumes. Okay. The last thing to look at is, well, a lot of chemical reactions take place in aqueous solutions, but a product in that chemical reaction is actually a gas. So here is an example of that. So our question is how many milliliters of hydrogen gas will be generated from or by reacting 0.914 grams of zinc solid with 50 milliliters of 0.650 molar HCl at, in this case, standard temperature and pressure. So here we have an amount of zinc and we have an amount of hydrochloric acid. The first thing we need to do is actually write out a chemical equation for this. And so this is actually a redox equation, a redox reaction. So stuff that we did in chapter 4, just not so long ago. In this particular chemical reaction, we have zinc solid plus HCl aqueous reacting to form H2 gas, and the product here is going to be zinc chloride. And zinc is one of those substances that really only exists as an ion in its +2 form. Okay, so it's going to be zinc Cl2, and that's something that you should have a feel for based on the ions that we talked about when we looked at type 1 cations back in chapter 2. Okay, so this is one of those type 1 cations that is not in the alkali metals or alkaline earth metals categories. And so here we just want to make sure this is balanced, so we need the 2 in front of the HCl, and that's our chemical equation for that reaction. From here, we need to now, we notice that we have some amount of one reactant and some amount of a second reactant, and we want to find out how much of this product we actually make. And so this right here is a limiting reactant question. And so we want to figure out how much hydrogen can we make given a starting amount of zinc, okay, and how much hydrogen we can make giving a starting amount of HCl. So we're going to start with our zinc. So from the zinc, from the 0.9.
Professor?
Yeah.
Can you repeat exactly what you were going to do just now? How much can we make? Can you say that sentence one more time? Sorry.
Yeah, we're trying to figure out how much hydrogen gas we can make, given we have either a starting amount of zinc or a starting amount of HCl, right? That's our limiting reactant right here. And we can look at this and say, oh, we're given a certain amount of zinc and we're given a certain amount of HCl. And since we're given different amounts of that, we don't know if they're stoichiometric amounts or not. So we should be determining how much H2, how much of that product we can make given the initial starting amount of each of these things. And whichever one gives us less is our limiting reactant, and that's going to be what limits us to however much hydrogen we can produce from that reactant. And so starting with zinc, right, we have a mass, so we need to convert that to moles by dividing by the molar mass. So the molar mass of zinc is 65.38 grams of zinc. Hold on a second. Grams of zinc per mole of zinc. All right, so the grams are going to cancel. We have our calculation is now in units of moles of zinc. And so here we know based on the mole ratio that for every 1 mole of zinc that we use, we get 1 mole of hydrogen. Okay. And based on the relationship that standard molar volume at STP, we know that for every 1 mole of H2, we get 22.42 liters of H2. And so we can track our units, right? We can see that we should be in units of volumes in terms of liters at the very end here. And so we wind up with, if you do that calculation, 0.3134 liters. Okay. We got to do the same thing for HCl. Only here, to get to moles, we're now taking the volume times the concentration. So 0.0500 liters, right? That's our 50 milliliters. So I'm converting directly into liters as I write it down. Multiply that by the concentration, Maya, you have a question?
Yes, that's 0.3134 liters of hydrogen gas.
Yeah. Yeah, there you go. Okay, so on HCl, we multiply the volume times the concentration. So 0.05 or 50 milliliters, 0.0500 liters times 0.650 molar or moles of HCl per liter. Right, so those will go away. The liters cancel out. We're left in moles of HCl. We see though that our mole ratio has 2 moles of HCl used to produce every 1 mole of hydrogen gas. And then we can multiply that by the standard molar volume, 22.42 liters per mole of H2. Right. And this one, if you do that calculation, you wind up with 0.3643 liters of H2. That's a 4. Is that a question?
Quick question. Molarity is grams per mole, basically, right?
No, molarity is moles per liter. Right, it's moles of solute per liter of solution. Right, so this right here, this value here, right? That 0.650, right? That's 0.650 moles of HCl per liter of solution. Right? That's what that one is right there. Okay. From this, so from our calculation, we've determined the value of H2, the amount of H2 that we can make from zinc, and we've determined the amount of H2 that we can make from HCl. We take our smaller value that tells us that zinc is a limiting reactant. Okay, so if zinc is the limiting reactant, then we can say that, well, we only make 0.3134 liters of H2. And if we look at our sig figs, we should have 3 sig figs in this value. And so it's also asking us for specifically how many milliliters. So we got to convert liters to milliliters, and we want only 3 sig figs. So that's going to be, we multiply that by 1,000 milliliters per liter. So we get 313 milliliters of H2 at STP. Okay. And that, so that right there is the last of the examples that we're going to do today on this stuff. I'm actually going to bring something into this. We're going to add a slide in here and talk about just a really simple, simple thing. Okay. So the other thing we're going to add in here that I want to talk about now is the density of a gas. Okay. So with the density of a gas, if we know density, right? Density is equal to mass over volume. Okay. So when it comes to the density of a gas, one thing we know about gases, right? Gases, if I have a gas, the number of moles of that gas in a certain volume is going to tell us something about the number of particles in that volume. Okay. Now, when I think about N of the gas, right? N is our moles of gas. Okay. And if I know the number of moles of gas, so if I know the N over V, okay, that right there, right, is the moles over the volume. I can use that to convert that to density. And I can convert it to density by multiplying the moles by the molar mass. Okay, so N times the molar mass, which is grams per mole, right? Those are going to cancel, and that's going to give me a density. Okay, so when you have an ideal gas, you can calculate the number of moles using the ideal gas law, but the density, in order to calculate the density of a given gas, you actually need to know the molar mass of that gas. Yeah, my question?
Yes. So just for chapter 5 specifically, N will mean moles, so not little m anymore, just to make sure that we're writing the right. Because N right there is equals moles, and we've been using little m for moles.
No, the abbreviation for moles is MOL, right?
MOL, okay. But
Yeah.
so now do we use N?
You can use N or you can use MOL, but if you see N, right, anytime we're using gases, right, if you think about PV equals nRT, right, and which is kind of another thing to get into, right? here, that N is always moles, okay? And so one thing you can do here is you can actually look at finding, in order to find the density of a gas, you can calculate N over V by rearranging the ideal gas law to be P over RT, okay? And so you can figure out the density of a gas from this if you know the pressure over RT, the pressure and the temperature, you can figure out the density of a gas, okay? And so the larger the molar mass, the greater the density, assuming the same pressure and temperature, right? So molar mass is proportional to the density of the gas. Okay, and that's just something I wanted to point out. It's actually a fairly straightforward concept, right? If you have something that's heavier, assuming you have the same number of particles in it, which is your N, the thing that's heavier is going to be more dense. Okay. And so with that, actually, we're going to end our the lecture component a little bit earlier today, and we'll pick up with this stuff for tomorrow. So the quiz on Thursday is through today's material. And then we've got, right now, we have the lab. So I'm going to stop our recording right here.